This is the 6th video of a 7-video series on hypothesis testing, two means. Here's an example of a claim about two means. Suppose we were to claim that the average cost of a Toyota is not the same as the average cost of a Honda. Now notice we're not saying here that one is higher than the other, simply we're claiming that their averages are different. And we want to test this claim with a 5% significance. What does that mean? Well, to understand that, you have to understand what a type 1 error or a false positive means in this context. Suppose we were to go pick random samples of Toyotas and Hondas, and we were to find that the sample averages were far enough apart, or so we thought, to prove that the average costs population-wide are in fact different, as we're trying to prove. But what if the only reason that the sample averages were so different is by random chance, and that in fact the average costs were the same? Well, we wouldn't know, but if that were to happen, we would call that a type 1 error or a false positive. Data that leads to a conclusion that isn't actually true. When we say we're going to test this claim with a 5% significance, we mean that we're going to set out from the beginning that we will accept this claim if the probability of a false positive ends up being lower than 5%. So we've collected our sample data. Notice here that if you compare the average costs in the samples, that there's a $400 difference between the sample averages. The question we have to address is that $400 difference statistically significant enough to support this claim that the average costs between the two companies are in fact different? So let's embark on our 5-step process, the first 2 of which are done for us here. And if you're a statistics student in a classroom setting, then it's typical that steps 1 and 2 have been done for you. There's been a claim, a stated significance, and the sample data has been, quote, collected for you, which could mean the professor actually collected sample data, or it could mean that it's just fabricated data for the purposes of classroom instruction. Either which way, steps 1 and 2 are done for us. So we go to step 3, which is really our first step, where we assume, contrary to the claim we're trying to prove, we assume that the average costs actually are the same. That's what we mean by assuming equality. Why do we do this? Because if we can make an assumption called the Null Hypothesis, and that assumption mathematically leads us to this $400 gap not likely to have happened by chance, then we can assume that our assumption may have been wrong in the first place, which will turn our favor towards the alternative hypothesis, that which we were trying to prove in the first place. So under the assumption of equality, that Toyotas and Hondas have the same population average, we're going to look at a sampling distribution of what Toyota sample minus Honda sample might look like. Now when I write x bar Toyota minus x bar Honda, I don't mean the particular numbers in our data. I don't mean the 26,500 and the 26,100. That difference is clearly 400. What I'm looking at here is something more general. I'm looking at a sampling distribution of what the sample average differences might look like if we were to repeat this same random sample multiple times. In other words, if I were to repeatedly take 60 Toyotas and 35 Hondas and subtract their sample averages, I would get a distribution that might look something like this. Now, under the assumption of the null hypothesis that the two companies actually have the same average, what would the sample average difference look like? Well, in some samples, the Toyota average would be higher, as was the case in our particular sample, but in other samples, the Honda average might be higher, and that would make this subtraction a negative number. But overall, most of the sample differences would tend to cluster around 0. That is, assuming the null hypothesis is true and that they're equal cost. So the question we have to entertain here is this $400 gap near 0, statistically speaking, in which case there wouldn't be enough evidence to support this claim, or is it significantly far enough away from 0 where it's unlikely to have happened by chance given the null hypothesis? That's what we're going to address here when we move on to our second step, or fourth step overall, finding the probability of this $400 gap. So we have a claim here regarding two means, and for our standard error, we're going to use this formula. Our test statistic will, as usual, be the number of standard errors that our $400 gap represents, and we're going to use the normal distribution here because it's assumed that we know the population standard deviations. And normal CDF will, as always, give us the probability of this $400 gap in samples. So plugging in all the numbers that were given, we have a standard error of about $233. So now the question is, how many standard errors is our $400 gap? Well, we divide to find that out, and find out that our $400 gap in samples is about 1.7 standard errors. And the normal cumulative distribution function tells us that 1.712 standard errors is pretty rare in that it only happens in about 4.3% of samples. Now, note that this is what we call a two-sided claim. If you've been watching the video series up to this point, we've only seen one other one of these. A two-sided claim is where you're comparing two quantities, and rather than saying one is bigger than the other or one is less than the other, we simply claim that they're not equal to each other, not stating that one particular one of the two groups is higher than the other. And whenever you have a two-sided claim, you have to double the probability. Why is this, and what does that mean? Well, the 4.3% represents the probability specifically that the gap is more than $400 with the Toyota sample average being higher. So let me restate that. The 4.3% represented the probability that the Toyota sample average would be more than $400 more than the Honda sample average. But if there's a 4.3% gap, probability of a $400 gap in favor of Toyota, there's also a 4.3% probability in favor of a $400 gap where the Honda sample average is higher. And that's why we double the probability here. By the way, if that logic gets lost on you, simply ask yourself this question. Is this claim favoring one side or the other? And in the case where we're saying that the Toyota average and the Honda average are not the same, which is this claim, there's no leaning to one side or the other. We're not saying one is higher than the other or lower than the other. And therefore that makes it a two-sided claim, and we have to double our probability here. Now, let's move on to our conclusion. We set out in this problem with the notion that if the probability of a false positive was 5% or less, that we would accept the claim. But what the calculation shows is there's actually more than 5%. There's an 8.6% chance of a false positive, counting both directions. And therefore, since 8.6 is higher than 5, we do not have sufficient evidence to support the claim that Hondas and Toyotas have different population average costs. By the way, it certainly is possible that they do have different population average costs. We just don't have the evidence in these particular samples to support that. Here's another claim comparing two means. The claim is that Mrs. Q's students are better at the quadratic formula than Mrs. R's students. The reason why this is a claim about two means is because suppose that these two teachers both have, say, 150, 200 students, whatever it is, and those are the, quote, populations. And this claim is essentially saying that if we were to test all of the students on the quadratic formula, that Mrs. Q's average or mean for her entire population would exceed that of Mrs. R's. That's the claim being made, and that's why it's a two-mean comparison hypothesis test. And we're going to test this claim with a significance of 10%. Again, that means we're willing to accept up to a 10% probability of false positive or type 1 error, and if that happens, then Mrs. Q wins, basically. So here's the sample data that we collected. Rather than giving quadratic formula tests to all 300 to 400 students that they have together, we give the test to 7 of Mrs. Q's students and 10 of Mrs. R's students. And here is the sample statistics that we found from that exercise. Now notice that there's an 8-point gap between the two teachers. In other words, Mrs. Q's students in the sample beat Mrs. R's students in the sample by 8 points. That number is going to be important later when we try to figure out the probability of such a gap. So back to our 5-step process where we start on step 3. We've made a claim, we've stated our significance, we've gathered our random sample. Again, if you're a statistics student, then the classroom teacher or professor has probably provided you with step 1 and 2. So we'll start with step 3, assuming equality. In other words, in this case, assume that there is no difference between Mrs. Q's and Mrs. R's students, that the populations as a whole are equal at the quadratic formula. We're doing this assumption. We don't know it to be true, but mathematically it's important to make this assumption, because if we make this assumption and then we compare the two samples from the two teachers, and we find out that that 8-point gap is unlikely to have happened by chance, then that will throw some doubt on this null hypothesis that we're making here, this assumption of equality. And throwing doubt on that may cause us to lean in Mrs. Q's favor and accept the alternative hypothesis. So, in the spirit of the mindset of equality, let's look at a sampling distribution of what Mrs. Q's sample averages minus Mrs. R's sample averages might look like. Now again, I don't mean here 85 minus 77. We know there's an 8-point gap in our particular sample that was performed. I'm looking more generally in my sample distribution and imagining what would happen if we continued this process multiple times. Of course, this is not practical to actually do. Mrs. Q and Mrs. R aren't going to continually pick 7 random and 10 random students respectively and continue this process over and over. The whole point of statistical sampling is to do it once. But imagine that we were to repeatedly take samples of 7 and 10 students from each. every time we did this, we would get different class averages. And assuming the null hypothesis, in other words, assuming that both classes are equal, then sometimes Mrs. Q's students would win and sometimes Mrs. R's students would win, and this difference, Mrs. Q minus Mrs. R, would tend to have lots of clustering around 0, if in fact the null hypothesis is true. The question we have to ask is this 8-point gap close to 0 or significantly far enough away from 0 to crown Mrs. Q the winner of this competition, as it were? So we'll go on to our next step, the actual calculations of the probability of this 8-point gap occurring. We're doing a claim about two means. This time we're going to compute our standard error, but unlike the last problem where we used population standard deviations to compute this, we don't have population standard deviations here. And because we don't have population standard deviations, we will substitute the sample standard deviations in their place. Now, as you may know from previous videos or previous material in a statistics class, when we replace the population standard deviations with the sample standard deviations, we use a t-distribution rather than the normal or z-distribution in terms of calculating probabilities. So we're going to use TCDF to calculate the probability of this 8-point gap. So here I'm plugging in the numbers that I've been given. I have a standard error of about 5.3. And what I need to know now is how many standard errors is our 8-point gap. In other words, how many 5.267s are there in 8? Division will tell me that. And I find out that this 8-point gap represents 1.519 standard errors. And again, because the population standard deviations are unknown and we only know the sample standard deviations, TCDF will give us the probability of this 8-point gap happening by chance given the null hypothesis of equality. By the way, it's worth pointing out, not only is that about 9%, and that means that there is a 9% chance of a false positive, in other words, of us awarding Miss Q the winner when her class actually wasn't better. It's also worth pointing out that the degrees of freedom here is 6. When you're using the degrees of freedom, you may recall that it's 1 less than the sample size, but here we have 2 sample sizes. So notice the degrees of freedom is actually 1 less than the smaller sample. Mrs. Q's sample happened to be smaller. She had 7 students. 1 less than 7 is 6, and that's my degrees of freedom. Now, to state my conclusion, we were willing to accept a 10% chance of false positive or type 1 error. But we found through the calculations that the probability that Miss Q isn't actually better, but she just won by random sampling accident, is only 9%, and since 9% is less than 10%, then there is sufficient evidence to claim that Mrs. Q's students are better at the quadratic formula than Mrs. R's students. And that completes lesson 6 of 7.